So let us start the second talk. Speaker is Professor Katsura from University of Tokyo, and title of his talk is Counting Richelot Isogeny of Superspecial Curves of Genus 2. Please start.
Okay. So anyway, thank you very much for inviting me to the seminar of algebraic geometry in East Asia. And today I will explain how to construct Richelot isogenies of superspecial curves of genus 2 and count the number of such things. Anyway. So, and throughout my talk, let K be an algebraically closed field of characteristic positive characteristic. And we assume P is greater than or equal to 7. And we denote by GA the one-dimensional additive group over K. And so on GA, we have a Frobenius map, and we denote by alpha P the kernel of this Frobenius map. And this is a local group. This is a local group scheme, as is well known. And let E be an elliptic curve defined over K, and N a positive integer. Then we get to homomorphism from E to E multiplication by N. And definition, we denote by En the kernel of this homomorphism. Then elliptic curve E is called supersingular if reduced part of P torsion group is 0, not P torsion part. And this is equivalent to the condition that E contains alpha P. And also this is equivalent to the condition that Frobenius map is 0 on H1. And also this condition is equivalent to that the Cauchy operator on E on this space is trivial. And if otherwise E is called ordinary. And maybe throughout this talk, we use supersingularity curve. And next definition is we consider abelian variety, and if E is let E be a supersingularity curve, and if A is isogenous to E to G, G times the elliptic curve, then A is called supersingular. And if A is isomorphic to G times elliptic curve E to G, then A is called supersingular. And this definition does not depend on the choice of supersingularity curve, because if we consider 2G times the elliptic curves, then E1 cross blah 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 EG is isomorphic to this one. So this definition doesn't own the choice of supersingularity curve. And we consider non-singular projective curve of genus G, which is greater than or equal to 2. And then the curve C is called supersingular if the Jacobian variety JC is supersingular. And also, if the curve C is supersingular, is called superspecial if and only if Jacobian variety is superspecial. This is our main tool. And we first consider isogeny graph. What is this? This is for vertex, we consider supersingular elliptic curves. And the edges or arrows, we consider two isogeny. Two isogeny means a quotient by a two torsion point of elliptic curve. Then we get such. First, we take one supersingular elliptic curve, and we consider quotient two isogeny. This is two isogeny. So for each elliptic curve, we have three two isogenies because we have three two torsion points. And we consider anyway, we take one two isogeny, and we go to next supersingular elliptic curve, and again we take one two torsion point and consider two isogeny, and go to the next one, and so on. And finally, we assume finally we get to E dash. Then if we know this process, we can get to E dash, of course. But if you take elliptic curve E dash, then without this system of two isogenies, then it is very difficult to find how to connect by two isogenies from here to here. And using this one, using this structure, so it is difficult to find a way from E to E dash by connecting two isogenies. By connecting by two isogenies. And we can make a crypto system by using this fact. And really, by using this, cryptographer construct isogeny-based cryptography. And this is really a candidate of post-quantum crypto system. And cryptographers examine such structure very deeply. And this June, at the end of this June, there was a conference on cryptography, which is ANTS 14. And there, they explain the situation, the current situation of isogeny-based cryptography. And they showed some memes. First, isogenies in one-dimensional. So anyway, this is the case of elliptic curves. Then in this case, cryptographers examine very well in this situation. And many theories already exist, and the situation is a very peaceful situation. But isogenies in dimension 1 plus epsilon means genus 2 case or some other case, genus is greater than 2. Then now they actively investigate such situation, and many papers now appear. So something like fire around him. And this is a welcome station. This is a welcome station. And he said, it's very fine. So now, we now examine the case of genus 2. And we consider graph of superspecial curves of genus 2. So anyway, instead of supersingular elliptic curves, we consider the following. For vertices, we consider principally polarized superspecial abelian surfaces. And for edges, we consider two isogeny. And then the structure of principally polarized superspecial abelian surface is as follows. Means long ago, Andre Bayou showed this is if A theta is a principally polarized abelian surface, then we have two cases. And one case is this is isomorphic to Jacobian of genus to curve, or A is isomorphic to product of two elliptic curves, and which is transversely intersect, and theta divisor is product of theta divisor is how should I say, E cross 0 plus 0 plus E2. This is decomposed. And this case, we say non-decomposed case, and this case we call the decomposed case. And we consider Richelot isogeny. I give the definition of Richelot isogeny. First, we consider two principally polarized abelian surfaces. This is not two principally polarized abelian surfaces. And we consider isogeny from A to A prime, such that pullback, this is pullback. Pullback of C dash is numerically equivalent to 2C, 2 times C. Then in such a situation, the isogeny pi is called Richelot isogeny. And really, this notion is appeared in 19th century. Richelot found this notion using elliptic integral. Anyway, we use such a notion. And in this situation, kernel of this isogeny is isomorphic to Z over 2 cross Z over 2. This is called 2-2 isogeny. And the problem is we need to consider the graph of such genus 2 curves. So the first problem is how many vertices are there? And also how many edges are there? So we solved such problems. And for vertices, long ago, Ibukiyama, myself, and all show the following. The number of superspecial curves of genus 2 is given concretely by like this. N0, for N0 to N6, I'll explain later. But anyway, the total number is equal to this one. P is, of course, characteristic of the field, base field. And this symbol is the Legendre symbol. And also, this is a non-decomposed case. And for decomposed case, the number of principally polarized superspecial abelian surface is equal to this number. Here, H is the number of supersingular elliptic curves. So already we know the number of vertices in this case. And now we give a definition to isomorphic of two Richelot isogenies. So we consider 3 principally polarized abelian surfaces. And we consider Richelot isogeny from A to A prime and A to A prime, 2 Richelot isogenies. And for these 2 Richelot isogenies, we say they are isomorphic to each other if there exists isomorphism, automorphism from here to from A to A, and also there exists isomorphism from A dash to A2 prime, such that, of course, pullback of which preserves the polarizations, and this diagram becomes commutative. Then these 2 Richelot isogenies is said to be isomorphic. And now see a non-singular projective curve of genus 2, and this is Jacobian variety, and she is canonical polarization of this Jacobian variety. Curve C is of genus 2, so anyway, C is hyperelliptic, so we have the hyperelliptic involution, and the quotient by hyperelliptic involution is isomorphic to P1. We have such diagram, such morphism. And for this morphism, it is well known, of course, everybody knows, I think, but we have 6 ramification points on C, and also we have 6 branch points here like this. Qi is the image of Pi. And we denote by C the group of automorphisms of C, and this subgroup generated by involution is the normal subgroup of this automorphism group. And we denote by the quotient of automorphism group of C by this subgroup. And this is called the reduced automorphism group, reduced group of automorphisms of C. And we have surjective map from O to C to reduced O to C. And if you take one element sigma, then of course there exists, you can find the automorphism here such that the modulo involution is equal to sigma. And the definition, element here of order 2 is said to be wrong if this one is also of order 2. Otherwise, sigma of order 2 is said to be short. We use this definition. Then, this definition does not depend on the choice of lift, of course. It is not a difficult thing. And anyway, theorem. Element sigma acts on freely on 6 branch points, then we can show sigma is wrong. Very easy to show, so I'll show. Anyway, by a suitable of choice of A1, and we can take 0 as a fixed point of sigma. And automorphism sigma is given by like this. And then the branch point is given by like this, with taking suitable A and B. And then the curve is defined by like this. So sigma is given by like this. So you can take sigma tilde like this. So this is, we can take sigma tilde of order 2. So sigma is wrong. Very easy lemma. And next, if reduced automorphism group has an element of order 2, then there, even if this is not a wrong element, then you can find there exists a wrong element tau of order 2. This is also not so difficult, but anyway, if sigma acts freely on 6 branch point, then I already showed here, sigma itself is a wrong element of order 2. So we may assume branch point is one branch point, Q1 is a fixed point of sigma. Since sigma is over 2, we have one more fixed point because we have six branch points, and one of them is fixed by element of order 2 by sigma. So we have one more fixed point among the branch point. So say Q2. Then by suitable choice of X, we may assume Q1 and Q1 is 0 and Q2 is infinity. And sigma is given by like this. We may assume sigma is given by like this, and Q sign is equal to 1. We may assume. Then the 6th branch point is given by like this. So the curve C is given by like this. And we consider element of O to P1 defined by like this. then this belongs to reduced automorphism group of curve C. And we have an automorphism tilde defined by like this. Then this is automorphism of C, and tau is of order 2. So tau is long. So if you have one element of order 2, then we can choose, we can find a long element in reduced automorphism group of C. Very easy. So construction of Richelot isogeny, how to construct? So we consider abelian surface, and this is dual of abelian surface, Picard group of A. And for divisor D on A, we have homomorphism like this. This is well-known homomorphism. Here, TV is translation by V. And we denote by KD the kernel of this homomorphism. Then, maybe by the theory of Mumford, or maybe you'll find the theory in the textbook of abelian variety by Mumford. We have a bilinear form on this kernel, non-degenerate bilinear form. And let G be an isotropic subgroup of KD, subgroup scheme of KD with respect to this bilinear form. If D is ample, then KD is finite, as is well known. So G is finite. So we have isogeny like this. And descent theory, for example, you can consult Mumford's abelian variety. If let Z be a isotropic subgroup of KD, and then there exists a divisor D dash D prime on here, such that pullback is D. So if you make quotient by isotropic, maximal isotropic, this is maxitropic, anyway, isotropic subgroup is okay. If G is the isotropic subgroup, you can descend to D from A to A over G. This is descent theory by Mumford. And we apply this theory to our case. And A is abelian surface with principal polarization C, and we consider 2 times C. Then this is the kernel of this, and this is the kernel of 2 times phi C. And so this is C is principal polarization. So this one is isomorphism. So kernel is trivial. So this is this one is just equal to the group of 2 torsion points. And we consider G a max. We take a maximal isotropic subgroup of K2C with respect to this pairing, and we denote it by G. Then the order of this is given by square of this order of this is equal to full subgroup, full group this. So this is equal to 2 to 4 fourths. And so G is isomorphic to G, Z over 2 cross Z over 2. So we get to Richelot isogeny. And by descent theory, we can find C dash on here, such that pullback of this is a linear equivalent or numerical equivalent to 2C. And the definition, if C dash here, if we can take C dash as a non-singular curve of genus 2, then we call pi a non-degenerate Richelot isogeny. And if C dash becomes a product of, consists of 2 elliptic curves, then in this case, we call pi a degenerate isogeny. And as a remark, the notion of Richelot isogeny is invertible. I mean, if you take image of two torsion points here, and we denote it by G prime, then G prime is isotropic subgroup here. C dash is principal polarization here. And so if you make quotient using this one of this, then this is isomorphic to A over group of two torsion points. So this is isomorphic to A. And we can also take isotopic subgroup here. So finally, here is return back to the original one. So if you can make, if you have Richelot isogeny from here to here, then you can find the Richelot isogeny from here to here. So notion of Richelot isogeny is invertible in a sense. And from here on, for principal polarization like this, we denote it by E plus E2 for the sake of simplicity. And if we say, we sometimes call E1 cross E2 a principally polarized abelian surface, then in this case, this has a principal polarization like this, E1 plus E2. This is notation. And so now, from here on, we assume C is a supersingular curve of genus 2. Then first main theorem, which I show, is total number of Richelot isogenies up to isomorphism outgoing from the irreducible superspecial curves of genus 2 is in total equal to this number. And also total number of decomposed Richelot isogenies up to isomorphism outgoing from irreducible superspecial curves of genus 2 is equal to like this. This is the decomposed Richelot number of decomposed Richelot isogenies, and this is number of non-decomposed Richelot isogenies. So next one is the total number is non-decomposed Richelot isogenies up to isomorphism outgoing from decomposed principally polarized superspecial abelian surfaces is equal to like this. So the starting point is now here, decomposed principally polarized superspecial abelian surface. And also the total number of decomposed Richelot isogenies up to isomorphism outgoing from decomposed principally polarized superspecial abelian surfaces is equal to this number. This is the main theorem in my talk now, today. And now, to show this one, we consider first a supersingular curve of genus 2. Then a reduced automorphism group acts on 6 branch point. And so 6 branch points. So this contains in S6 permutation of 6 branch points. So, and also RC reduced automorphism act on project line P1. So this one is a subgroup of PGL2K. This is automorphism of P1. So this one is contained this reduced automorphism group is a subgroup of this group. So using this, we can make a list of a finite subgroup of this. So using this, we can make a list of reduced automorphism group. This is like this. And this one is already proved by IGSA long ago. And also specialization relation is known by IGSA. So this is case zero. So no reduced automorphism group. And by specialization, we get bigger reduced automorphism group like this. And I already showed something, but we denote by Ni the number of superspecial curves of genus 2, whose reduced automorphism group is isomorphic to the group AI. Group I means group like this here. I. Then the number of superspecial curves of genus 2 is given by like this. N0 is equal to this one. And of course, for example, this is Legendre symbol. And N1 is equal to this, N2 is like this, N3 is like this. Okay, this is a list of number of superspecial curves for each class. And how to, anyway, I will show how to compute the number of superspecial curves for each class. So I will show only example, but we consider two cases. Curve C alpha is genus 2 curve. I should write RAC alpha, but alpha is omitted, which contains S3, and C beta is curve of genus 2, whose reduced automorphism group contains this group. Then it is easy to show such curve is has such normal form. Also, this curve has such normal form. It is not difficult to show. And we can check when they are isomorphic to each other. If you give alpha and alpha prime, for example, then C alpha isomorphic to C alpha prime, if and only if this or this. C beta is also the same. And we consider the polynomial like this. This is Gauss symbol, means integer part of this rational number, integral part of this rational number. And we calculate Katsura operator for curve C alpha and C beta. So we calculate Katsura operator with respect to a base such to one forms. Then the Katsura operator of C alpha resp C beta is given as follows. We can get to such a matrix. And well-known fact, C is superspecial if and only if Katsura operator is 0 on this space. This is a criterion of superspeciality. And so, when this matrix is 0, this is if G alpha is, if and only if G alpha is 0. So C alpha is superspecial if and only if G alpha equals 0. And also C beta is superspecial if and only if H beta is 0. And so now we need to check that these two polynomials has multiple root or not. For this purpose, we introduce hypergeometric differential equation. First, we consider this one over characteristic field of characteristic 0, and it is well known that this hypergeometric differential equation has such a solution. Such solution. Now we consider this solution in positive characteristic. So I cut off until p-1 term, degree p-1 term. We consider such polynomial. This is just polynomial. This is of course formal power series, but this is just polynomial. And then we set like this. This is constant, but we like this. Then we can show this one is equal to the solution here, like this. So for G alpha is equal to F0, A is 1/2 and B is 1/3 and C is 5/5, 6 modulo P. We have such equal congruence relation. And so this means GH and GX and HX are solutions of this equation. So GX, large GX is equal to GX over constant. So GX and HX are solutions of certain hypergeometric equation. And using this, we can show this G and H has no multiple roots. So we can count the number of superspecial curves in these cases. This is a method given by Igusa long ago to calculate supersingular elliptic curves, but such technique works also for genus 2 case, in this case. And so now we give an example of decomposed Richelot isogeny. First, we consider non-singular projective model of curve of genus 2 defined by equation like this. And iota is the hypergeometric involution defined by, which is given by like this. And we have also automorphism of element of reduced automorphism group. And this one has an element of order 2 defined by like this. So x2 minus x like this. And we consider composition of sigma and iota. And we denote it by tau. And no, these two automorphisms are long elements of order 2. I mean, these two elements act on branch points, how do I say, freely. And we consider a quotient of this genus 2 curve by automorphism of order 2, sigma and tau. We set like this. Then we have natural map from CAB to E sigma cross E tau. And by this, we have induced isogeny from this to this. Then we can calculate the kernel of this. Kernel of this is isomorphic to product of z over 2 cross z over 2. And the kernel pi is consists of such elements, divisor on CAB. And like this. And so we can conclude this one is decomposed Richelot isogeny with CA prime polarization here is given by like this. And also the elliptic curve E sigma is defined by like this with lambda. Lambda is given by like this. Using A and B, lambda is described. And also E tau is given by like this. Using by this function, we have a map. This map is a bijection from the set of AB to lambda mu, like this. This is bijection. So using by this set, anyway, we can count the number over here. So we can also count the number over here. number here. So we use this bijection to calculate decomposed Richelot isogeny. And the problem is when the Richelot isogeny become decomposed one. And our key proposition is like this. C is a non-singular superspecial curve of genus 2, then the following two conditions are equivalent. So C has a decomposed Richelot isogeny outgoing from JC, and this condition is equivalent to reduced automorphism group has a long element of order 2. So by this we see decomposed Richelot isogeny outgoing from JC is equal to the number of long elements of order 2. This is our key proposition, key lemma. Anyway, roughly I will explain the proof. So first we have a Richelot isogeny, and G is isotropic subgroup here with respect to 2 times C polarization. And then we have C dash is a principal polarization of 2 elliptic curves on decomposed. So decomposed here, C dash is decomposed polarization like this. So we have such linear equivalent. And C is principal polarization. We have an isomorphism from JC to dual. Similarly, we have this and this are isomorphic. JC over G is isomorphic to the dual of this dual. And so dualizing this situation, we have such situation, dualizing. And then this is dualizing situation. So pullback here is the polarization is decomposed, and here pullback of polarization C from here to here is becomes 2 times E1 plus E2. So we consider automorphism of iota cross identity here. On E1, tau bar is inversion, and E2, this is inversion, identity. Then this is not inversion of this Hubblian surface, but anyway, this is automorphism of order 2. And also, by definition, this one preserves the polarization. And also, this one is identity on kernel of eta. So this automorphism, we can make descent of this automorphism from here to here. So this one becomes automorphism of Jacobian of C, and this is not inversion. So this becomes automorphism of order 2 on this space, and we can show that this one is a long element of curve C. This is outline of our proof. And now, so the problem is we need to count the number of long elements of order 2 in reduced automorphism group. And so for reduced automorphism group, we express like this. Reduced automorphism group is an automorphism of P1, so we can express the reduced automorphism group like this. And X is a suitable coordinate of A1. And we use such notation, then we can list up all long element of order 2 for each cases like this. This is just list, and we need to compute very concretely, and we get the such list. And we have one corollary. For a curve of genus 2, the number of outgoing decomposed Richelot isogenies from JC is at most 6. This one is this one 1, 2, 3, 4, 5, 6. So this curve has 6 long elements. So using this curve, if we consider this curve, Jacobian of this has 6 decomposed Richelot isogenies. And anyway, this result is known by Katsura, Decru, Smith in the world of cryptography, but they use computer calculation, computer-aided calculation. So anyway, this gives a new proof of the result by Katsura, Decru, Smith. Anyway. And construction of isotropic subgroup. How to construct? And she is we consider the case of a non-singular project curve of genus 2, and we consider Jacobian and PI the ramification point of this natural map. And for fixed C, we consider set of pairs of Jacobian and isotropic subgroup for the polarization of 2C. Then it is classically known that division into the set of 3 pairs of these 6 points gives the isotropic subgroup G. So like this. This is isotropic subgroup for this. So number of isotropic subgroup of KC for fixed curve C is given by, we choose 2 from 6 and multiply by, we choose 2 from 4, and we need to consider permutation. So divided by 3 factorial, then it 15. So anyway, we have 15 Richelot isogeny from one Jacobian variety. And anyway, automorphism group acts on ramification point of this. And also iota acts on 2 torsion point trivially. Iota is inversion, is act Jacobian 2 torsion point of Jacobian trivially. So reduced automorphism group acts on this set. And anyway, action of reduced automorphism group on this set is given by the action of reduced automorphism group of such set, because pair of 2 ramification point gives 1 isotropic subgroup. And this set consists of 15 elements. 15 elements. For example, we consider one example. Take curve C of genus 2 with reduced automorphism group is isomorphic to Z over 2. Then such curve is given by the equation like this, and with suitable condition for AB, of course. If AB is very special, then the reduced automorphism group becomes bigger than this cyclic group. And we denote by branch points by QI. Then generator of reduced automorphism group is given by like this. Sigma is like this. And the sigma acts on this space. And anyway, this acts on ramification points like this. So exchange this, exchange this, exchange this. And this one gives decomposed Richelot isogeny, as I said. Already I showed the example. And the other isotropic subgroup gives non-decomposed isogeny. Okay. And for this situation, we denote by pi by I for the sake of simplicity. Then the action of sigma is given by the permutation like this. And so, reduced action of reduced automorphism group is given by like this. So calculating the orbit of this, then they have 11 loci. So anyway, reduced automorphism group sigma is a long element of order 2. So, and this one is fixed by sigma, and this one gives a decomposed Richelot isogeny, but the other 10 loci gives non-decomposed isogeny. So the proportion is, we can anyway calculate each, for each case, we calculate, we do such calculation, and we can make a list for orbits of reduced automorphism group on set of isotropic subgroups. And for example, if reduced automorphism group is isomorphic to 0, then it does not contain any long elements, so no decomposed one, and all orbit consists of 1 and 15 such exits. And if reduced automorphism group is Z over 2Z, then as I showed now already, 11 Richelot isogenies exist and 1 decomposed one. So we do not like this. So we can make list. And using this, we can show this result. The total number of Richelot isogeny up to isomorphism outgoing from irreducible superspecial curves of genus 2 is equal to this number. And also total number of decomposed Richelot isogenies up to isomorphism outgoing from the irreducible special curves of genus 2 is equal to this number, decomposed one. And the proof is just summing up our calculation until now, because for each class, number of superspecial curves we know. And for each decomposed one and non-decomposed one, we can calculate. We already calculated. So we summing up these things, then we get this number. And also this one gives this number. This is the calculation for Richelot isogeny outgoing from irreducible superspecial curves of genus 2. Now we go to Richelot isogenies from elliptic curve products. Then this is also the almost same method we can use, and we consider Richelot isogeny from here to here. And we denote by O to E cross E, the group of automorphism of this which preserve polarization. And we consider 2 torsion points on E dash, E prime, and 2 torsion points of E. Then this point exist on product like this, like this. This is E prime, and this is E, and 2 torsion point 3 here, and 2 torsion point 3 here. And so, how to make isotropic subgroup G? Then, very similarly, we can see this one gives an isotropic subgroup of 2 torsion points on this abelian surface. This is very parallel to the case of super special curves of genus 2, genus 2 case, curve case, irreducible curve case. And also, this one acts on this two torsion point here. And we consider two special elliptic curves. E2 is elliptic curve defined by this equation, and this automorphism group is isomorphic to Z over 4Z for this. And we denote by E3 the elliptic curve given by this equation, then automorphism group of E3 is given by this. And then the result is very similar to the case of irreducible curve of genus 2. And anyway, we consider the orbit on isotropic set of isotropic subgroups and consider the locus, then we get such a very concrete result. And we denote by H the number of super singular elliptic curve and H1 the number of super singular elliptic curve E with this automorphism. E2 is the number of super special super singular elliptic curves with this automorphism, and the number of super singular elliptic curve E3 with this automorphism group such. Then, of course, concretely, we can express these numbers. This is very famous formula for the number of super singular elliptic curves. And this is the number of super singular elliptic curves with automorphism, this automorphism, etc. Then total number is, of course, equal to H. And now the total number of non-decomposed Richelot isogeny up to isomorphism outgoing from decomposed principally polarized superspecial abelian surface is equal to this number. And also, how to say, total number of decomposed Richelot isogenies up to isomorphism outgoing from decomposed principally polarized superspecial abelian surfaces is equal to this number. And the proof is very similar. For each case, we consider the number of Richelot isomorphism up to isomorphism, and we summing up. We sum up these things, then we get the result. And finally, we give some example. This is a case of characteristics 7. Then in this case, we have only one super special, super singular elliptic curve, and only one super special curve of genus 2, like this. So, but we have two vertices, C and E2 cross E2, and this is Richelot isogeny. Outgoing one is 4, and ingoing is 6. 6. And some isogeny, Richelot isogeny go to the same vertices. So multiplicity is 4 here, and also multiplicity 4 here. But the total number here is always 15. And here is also the total number is 15. And the case of P is 11. Then we have two super special curve of genus 2 and two super singular curve of super singular elliptic curve. And also we have two special curves of genus 2, C1, C2. And so we have 3 decomposed one using this and this. And from here to here, outgoing Richelot isogeny is 4, and from here, outgoing Richelot isogeny is here, like this. This is diagram for Richelot isogenies. And finally, this is the case of P is 13. Then in this case, we have 3 super special curves of genus 2 and only one super singular elliptic curve. So the structure of graph of Richelot isogenies becomes like this. Okay, that is this is a reference of my talk. This is reference of my talk. Okay, thank you very much.
Thank you very much for your talk. Are there any questions or comments? May I ask one elementary question?
Yeah.
So the Richelot isogeny, what is the origin of Richelot isogeny? This is purely mathematical origin or crystallographical origin?
Richelot isogeny is originally come from elliptic integral. So 1836 or something, Richelot found it relation. And then, for example, recently to construct the Enriquez surface, Mukai used this isogeny, Mukai. But recently, a cryptographer, how do I say, used this one to construct post-quantum crypto system. But it's very important because maybe in some years, quantum computer will be invented. Then crypto system now is almost all crypto systems are broken. So they are going to make such a system for future. Yeah. So this is one candidate. Isogeny-based crypto system is one candidate for it. Yeah. But anyway, I'm not a specialist for cryptography. So from viewpoint of mathematics, I, how do I say, examine these structure. Yeah.
Then, for example, from purely mathematical viewpoint, not only Richelot isogeny, but other order isogeny is also interesting.
Yeah. Yeah.
If
also,
one will do something for this.
Even in world of cryptography, not only two isogeny, but also three isogeny also they use.
Yeah.
So, yeah. So several isogeny will be coming for the theory of cryptography also. Yeah. But Richelot isogeny is very, very fundamental one.
And such counting is open program for higher.
What kind of graph we can make? For example, Ramanujan graph or so, such type of things is, they have many open problems in the world of cryptography. Yeah.
Purely mathematical view.
Yeah, and graph theoretical, yeah, conjecture exists.
Thank you. Thank you very much. Are there any other questions?
Excuse me. So may I ask why this kind of graph is related to cryptography? So I'm very ignorant for this. So
at the beginning, I somehow explained using elliptic curve case, but if you start one vertex and go to the different vertex, how should I say? It's very difficult to find the root, and using the difficulty to find the root of Richelot isogeny, we can make cryptography. For example,
so I understand the difficulty, but somehow it should be also easily calculable if you want to construct. Yeah. So if you know the answer, then it should be easily handled.
Yeah.
On the other hand,
but no one knows. So
No. So
Yeah.
this is breaking the cryptography. But if you want to make a cryptography, then it should be easily constructed. Huh?
Mhm.
So why it is easy? So if you know some clue beforehand.
The technique is how to, for example, in the case of elliptic curve, for example, J invariant is, how do I say, secret thing. And first you start one elliptic curve, then everybody knows the J invariant there. And we need to exchange, two persons want to exchange some number. So first for example, first you consider sequence of two isogeny, and you get to different J number, J invariant. And for example, to different, we consider three isogeny and get to, how do I say, different elliptic curve, then exchange these two J invariant each other, then each person do same procedure using the J invariant and go to the same J invariant. So by such a technique, you can get to, two persons can get the same J invariant, and no other person can guess what is the J invariant. Such type of technique we can construct in the world of cryptography. Yeah.
Okay, thank you very much.
Are there any other questions or comments? If not, thank you very much again for your nice talk.
Yeah. Then go out.
Now we are over.
Okay.
Okay, and thanks to everybody for the participation. And our next seminar will be 2 weeks from now.
Yeah.
Okay, so see you next time then.